morning, folks. Welcome to session 7, which is on monitoring and measurement. We have an exciting lineup for you today with 5 papers, and we hope to do some timekeeping on that as well, so that you can go to your lunch on time. The first paper in the session is on continuous in-network round-trip monitoring. The work will be presented by Satadal Sengupta. Sata is a 4th-year PhD student at Princeton, advised by Jen Rexford. And his research revolves around enabling fine-grained measurements using the high-speed programmable data plane. And I also heard he likes to ride a motorcycle in his spare time. The artifacts associated with this paper have been evaluated as reproducible, and the code is released as open source on GitHub. Go ahead.
Awesome. Thank you so much. So good morning, everyone. I'm going to present our paper, Continuous In-Network Round-Trip Time Monitoring with Dart. Today, this is joint work with June Kim and Jennifer Rexford from Princeton University. And if you are wondering why there's a glass of red wine in the corner, that's because our group is called Cabernet. And if you have more questions, you can talk to Jen about it. So let's get started. Continuous RTT monitoring is useful. So let us take an example and see how it can be useful. So let's assume there is a client and a server talking within the US. And I'm sorry, my clicker is weird. Oops. Fallback. So let's say there is an adversary in Europe that is trying to snoop in on this particular communication, and it launches a BGP interception attack against this communication, and the data is rerouted via him. And he might want to do this to perform web fingerprinting or steal cryptocurrency and so on. So these attacks can be really sneaky, and they may not be detectable using traditional methods. But we notice that this data actually is rerouted over an extra distance of 15,000 kilometers, which is at least 50 milliseconds more round-trip time. So wouldn't it be nice if we could use this information to somehow detect and stop this kind of an attack? And this is just one example of how RTT monitoring is useful. So what do we really need to perform this kind of detection? First, we need to compute RTTs in real time, because the more you wait until you detect something, the more the attacker intercepts useful, sensitive packets. We want to monitor RTTs continuously throughout the lifetime of the connection, and not just at the beginning during handshake or periodically. And we want to measure RTTs accurately, because false positives can raise false alarms, and worse yet, false negatives can lead us to miss these attacks. So traditionally, there are 2 RTT measurement techniques. Active measurements, think ping or traceroute. There is a measurement host that sends a probe across to the server, and the server responds, and the time difference gives us the RTT. This is great for characterizing the network, but when it comes to getting user-experienced round-trip times, or when it comes to getting real-time or continuous RTTs, it's not that great. The other option is passive measurements, and here you let the client and server talk to each other as they would normally, but you measure RTTs at a certain vantage point between the client and the server. And this is great for user-experienced RTT, we get that, but to get real-time and continuous RTT, we have to do the passive measurements in the right place and in the right way. So what are our options to do passive RTT measurement? We could do it at the end host, right? But to do it at the end host, we have to install special software hardware at the clients, and or if a campus operator or enterprise operator wants to do this, they would have to get permissions from the clients. So it's better to measure at an aggregation point, like the edge of the campus network. Can we do it only with TCP handshakes? Well, connections can be quite long, and RTTs can change over the lifetime of a connection. And also, handshakes are not always representative of the actual RTTs experienced by the user. So it's better to do per-packet measurement for the kinds of use cases we have in mind. And can we do it in software? Well, one option is to do offline, which is PCAP processing. And clearly, in our example, you cannot wait until the attack has already happened to capture a PCAP and process it. If you do it online in software, it will be slow. And if you scale it up, then it will be really expensive. So here is where the programmable data plane comes to our rescue. So what is the end goal? What is our vision with this? So let's say the client and the server are communicating, and there is a switch at the campus or enterprise edge. And let's be optimistic and say that this is a high-speed programmable switch, which is increasingly the case these days. And the switch does normal forwarding as it would, but in parallel, it can also do other tasks because it is programmable. And in this case, it does RTT measurement, and it sends a stream of samples out to an analytics and mitigation engine that then takes decisions on the traffic based on what the RTTs are. In this paper, we do focus on the RTT measurement engine. So how would you go about doing continuous RTT monitoring for TCP traffic? So here is the client and the server, and here is the high-speed switch. And so when a data packet goes from the client to the server, we basically keep track of the expected acknowledgement number, which is basically the TCP sequence number plus the packet length. And this is to match the corresponding acknowledgement coming back from the other side, and then calculate the time difference, which gives us the per packet RTT. And we can keep doing this throughout the lifetime of the connection, and it'll keep giving us RTT samples. Now, this should be trivial, right? It's just a matching of two numbers. But, well, TCP has some peculiarities because of certain features that it enables. So one of them is retransmission, and it can lead to ambiguities in how the RTTs are collected. And reordering is another source of ambiguities. And then finally, TCP also has cumulative hacking, which means that a lot of the packets do not even get acknowledged. And it keeps living, they keep living in the memory of the switch, which becomes expensive. So we call these the idiosyncrasies of TCP traffic, if you will. And we have to somehow balance this against the limitations of a programmable switch, which has limitations because it wants to be very fast. But with that comes the limitations that you cannot do complex math, there is limited memory, and it has a certain finite number of stages that you have to work with. So how do we design for correctness? So just a refresher, the challenges we spoke about in this context would be retransmission and reordering ambiguities. And our solution really is to store Perflow state so that we can detect these ambiguities and eliminate any kind of erroneous RTT sampling. So let's imagine that this is the flow sequence number space. It's divided into three components. The left part is already act. The ones are bytes in flight, essentially, transmitted but not act. And then the others are not seen yet. And we keep 2 pointers. The first one is the maximum byte acknowledged, and the second one is the maximum byte transmitted. And we define this as our measurement range, just to these two numbers. And then when there are ambiguities, we detect them like this. So if there is a data packet with bytes that you have already seen, we know that this is a retransmission. And when there is an ACK packet for something that has already been acknowledged, we count this as a reordering. And we say that the middle portion has now been affected by retransmission or reordering. And we basically collapse the measurement range. We point the left pointer to the right pointer and close the interval. And when that happens, we basically do not take any RTT samples, thus ensuring that the samples we actually take are valid and correct. And now the measurement range is max byte affected to max byte transmitted. And together, these two definitions can be combined into the left pointer being max byte act or affected, and the right byte being max byte transmitted. Now, we store Perflow state, but how do we then ensure that this is also possible to do in the programmable data plane, because memory is critical. So when a new packet comes in, we first have this range tracker table, which is storing the Perflow state. It stores the flow ID, which is basically a hash of the 4-tuple of the flow, and the measurement range, as I explained before. And then once it goes through this range tracker table, it either updates the measurement range or collapses the measurement range, depending on the case. And then if it goes through, as in if it's a valid packet, then the packet goes to a packet tracker table where the packet record is stored. So in this particular case, you'll see that flow F1 has 3 packets in the packet tracker table. The packet tracker table stores the flow ID as well as the expected ACK number to distinguish packets, and also the timestamp of each corresponding packet. And then finally, when an ACK comes back, we take the corresponding RTT sample. Now, this is challenging to deal with because TCP has cumulative ACKs, and many packets can have large RTTs. So because of cumulative hacking, what happens is some of the packets will never get acknowledgements, and they'll keep on waiting forever. But then because some packets have large RTTs, they have to legitimately stay on in the table for a long time. So how do we distinguish between these two cases and evict the first ones out but keep the second ones? And for example, let's say this one doesn't get any acknowledgement. So our strategy here is to use recirculation to check against the flow tracker whether a packet has become stale, as in has the measurement range moved on since that packet. And if it has moved on, then we drop the packet, and if it drop the packet record, essentially. And otherwise, we push it back into the packet record table. And we call this lazy recirculation with a second chance. Lazy because we wait until there are hash collisions to perform this process, and a second chance because the packets that actually have large RTTs have a second chance of living on in the packet tracker table. We also protect against thin flooding by not storing handshake packets. This is a design decision we take to not store state when we don't need to. And together, this system becomes Dart, which is nothing but data plane actionable round-trip times. This is implemented in the Intel Tofino and has been open sourced, so you can go take a look at it. Now we come back to our first example. How do we detect interception attacks in real time? So we actualized this particular attack by launching a BGP interception attack using the peering testbed. We had two clients, a client and a server talking between Princeton and Northeastern universities, and the adversary was, well, here in Amsterdam. And what we see is that Dart is able to produce continuous round-trip time samples. And as you see, like around the 36th second, when the attack is actually launched, the RTT goes up high, and we can actually use this information to then do useful stuff. So we implemented a simple change point detection algorithm offline on this particular RTT data, time series data, and we could detect the attack within just 22 data packets and 2 seconds of time, which shows that it is very effective. We also perform simulation-based evaluation because we want to sort of sweep the parameter space of the Tofino in terms of memory, number of stages, and so on. And for this, what we do is we capture a packet trace in our campus. This is an IRB-approved study, and the trace is anonymized. And we pass it through a version of Dart, which is implemented in Python. And we collect the RTT samples, and we then compare it against a version of TCP trace, which is a tool traditionally used to compute RTTs for packet traces. And this is sort of our baseline. And the takeaways that we have essentially is using only 24% of the sort of Tofino SRAM, we can get a really good performance. So if we have only one stage, then we collect around 99% of the samples with only 10% recirculations. And we can divide the memory up into multiple stages, like in this case 8, and we get almost all the samples with 16% recirculations. So what are the possibilities that this opens up? There can be many other in-network use cases. I only spoke about one, but we could do continuous monitoring in the enterprise or campus edge. We can do traffic engineering in real time, as in if network conditions go bad, we can steer traffic to a different route. And we can do server selection for, say, low latency applications like video conferencing or cloud gaming, et cetera. We believe that even though we use this design for RTT collection, this design is actually generalizable to an extent. And what basically this does is it gives us a way of doing a scalable join operation in the programmable data plane. So whenever we have to combine, sort of join two different directions of traffic, we can use this. And finally, our vision is to build a diagnostic tool. So Dart has this really nice feature, and you can read more in the paper, that it can measure different legs of the RTT, sort of telling us if there is a problem, where the problem is. And we foresee this as turning into a finger pointing as a service in due course of time. So we are working towards that. And thank you for your attention, and I'll take questions now. Thanks.
Thank you very much. Perfect timing. Do we have questions in the room? Yes, over here at front.
Oh, I have a question. Maybe I can start. I have the mic.
Okay, yeah,
Paola
sure.
Grossi, University of Amsterdam. I was curious about what next. So as a motivation, you want to detect attacks. How would you inform the users? Have you thought about it? And then going back to one of your initial motivation, you say you don't want to do this work of RTT continuous monitoring on the host, on the hand host, but you could argue you could also do it there. You have RTO calculation, timeout retransmissions. So how do you see the two things actually to make this usable, this information?
Right, thank you. That's a great question. So for your first question, we are actually, so at the time we wrote this paper, this detection was still not in the data plane, but we have worked towards a solution, so it can actually do detection and mitigation in the data plane right now. We are still working on it. It's a work in progress. We are working on more use cases, like, say, improving video QoE, et cetera. To your second point, it is true that the end host does this kind of course, does this kind of calculations. But this is more from the perspective of a campus or enterprise operator who wants to protect all of their users at the same time. So it's really cumbersome to install something everywhere. Rather, you would have it at a central point and enable multiple sort of use cases within the switch itself. So that's our vision. Thank you.
OK, over there.
How do you track RTTs for non-TCP traffic, like Quick or other UDP applications?
Right, that's a great question. So Quick has a spin bit that allows us to collect RTTs some of the time. So in any situation where you have sort of a sequence number and an acknowledgement number scenario, like even for RTP traffic, sometimes you'll have that. There, this will work. We do not do that in the paper, but we talk about such ideas. And then, in general, you can think that whenever there is non-TCP-based traffic, there is also some TCP-based traffic to the same server or server prefix. For example, with Zoom calls, you could be using chat, et cetera. Your session could be handled. And so TCP RTTs kind of augment whatever other information about RTTs you have. So this is sort of augmenting any other source of RTTs that you might have in those cases.
OK, then for TCP, how do you deal with other effects like delay acts?
That's a great question. Delayed acts, so any kind of delay introduced by the end host, like processing delay or delayed acts, is hard to deal with in this case. And that is a problem of any passive measurement tool, really. We have looked into dealing with delayed acts, and it's a very hairy sort of beast. So there is no easy answer to that. If you have any ideas, please come talk to me. I'd be glad. But we do not have a straightforward answer to that yet.
Thank you.
Anja?
Anja Feldmann from Max Planck Institute for Informatics. So a couple of quick questions. First of all, it seems like your assumption is that there is no lost packet on the side between the user and your first monitoring machine. Is that correct?
We assume that there is no reordering or loss downstream from the vantage point, yes.
OK, next question. How do you deal with selective acknowledgement, which are much harder to parse?
That's a great question. In this paper, we have not tackled that problem, but we have looked at the possibility, and hopefully we can extend this system to parse selective acknowledgements and do something useful with it, but we don't have an answer as of yet.
The next question is, what happens if you have not just a single router through which the packets pass, but multiple ones, especially if the return path is not the same as the original path?
Yeah, so that's an...
And thank you for the nice work.
Thank you so much. That's an assumption we have to take, that the switch sees both sides of the traffic, and really any passive measurement tool has to have that assumption in order to work. So thank you again for the question.
OK, let's thank the speaker.
Awesome, thank you.